All right, today we'll set out to answer this question. How do you differentiate a composition of functions? We've established rules for how to differentiate the sum of two functions and the difference of two functions. That's easy. We have a rule called the product rule for telling us how to differentiate the product of two functions, and the quotient rule for differentiating the quotient of two functions. But what if you combine together two functions f and g in this way? Y is f of g of x, right? This is composition. So how would we find y prime in this case? Well, to explore that question, we're going to do what we often do with a composition of functions, which is to break it down into two steps using substitution. So we're going to say y equals f of u, and in turn, u equals g of x. So setting it up like this produces what we call a chain of dependence in the variables. See if I can spell dependence correctly. Oopsie. Chain of dependence. So what I mean is that the value of the output variable, y, depends on the value of the middle variable, u, which in turn depends on the value of the original input variable, x. So we have this chain of dependence set up with three variables. Now, we're going to imagine a hypothetical scenario. Let's go into a thought bubble. Let's imagine, I'll use the word suppose. Suppose that for every change of one variable, one unit, whatever it is, let's call it an increase. For every unit increase, sorry, my computer is slowing down. For every increase in x, let's suppose that u increases by 2. And we're also going to say, suppose that for every increase in u, we know that y increases by 3. What these two pieces of information are doing is they're each giving us a derivative. Oops. Didn't plan this out quite as well as I thought. So this first piece of information is telling us that, that the rate of change in u with respect to x, in other words, du over dx, is telling us that that equals 2. 2 increases in u for every increase in x. And the second piece of information is telling us that for every increase in y, sorry, for every increase in u, y is increasing by 3. That's the rate of change in y with respect to u. That's equal to 3. That's what those two pieces of information are giving us. So now, if we go back to our chain of dependence up here, I'm going to write it down here again. We imagine coming along and increasing x by 1 unit. Let's follow the chain and see what happens according to our rules. We increase x by 1 unit, u is going to increase by 2 units. That's what the first rule says, right? So this will be plus 2. And plus 2 can be written as plus 1 plus 1. So that's 2 increases in u, right? Plus 1 plus 1. For each of those increases in u, y will increase by 3. So this will be a plus 3, which overall is a plus 6, right? So we can say that for every, for every single increase in x, we know y increases by 6. So this means that the derivative of y with respect to x is 6. And you'll notice all that happened here is we multiplied 2 by 3 to get 6. All right, so that is evidence part 1. Let's look at evidence part 2. This comes courtesy of our friend Mark Renault of Shippensburg University. So this is titled The Intuitive Notion of the Chain Rule. You're welcome to go check this out on your own. I put a link to this on D2L. So here we have the speed of the x wheel here. And this, I can make it slower or I can make it faster, that sort of thing. So right now, this is the x wheel, and the x wheel goes around once for every unit of time. Now, the radius of the x wheel is 8. What we're going to do is we're going to connect the x wheel and the u wheel by a chain or a belt. This happens with gears on a bicycle, right? You have like small gears, big gears connected by a bike chain. It happens inside your car with like drums and belts that are connected that spin. And the spinning of, now that these are connected by a belt, the spinning of the x wheel causes the u wheel to spin. But the difference in the radii make it so that one unit around the x, one time around the x circle is actually 4 times around the u circle wheel. The reason is because the x wheel is 4 times as big as the u wheel. Comparing these radii, we see the x radius is 8 and the u radius is only 2. So expressed in terms of a rate using calculus notation, this is the rate of change in u with respect to x is 4. For every single increase in x, which is interpreted as one turn around the circle, the u increases by 4 turns around the circle. Now, if you also connect the u wheel and the y wheel, we will see that for every, now let's just focus on those two. For every single turn around the u wheel, the y wheel only goes around 1/2 circle. If you want to see the y wheel go around 1 time, you have to turn the u wheel around twice. So, and again, this is because of the radii of the circles. So in terms of calculus, in terms of rates, that means that the derivative of y with respect to u is only 1/2. It goes around half as fast as the u wheel. So the chain rule asks the question, now that these variables are chained together in this way so that y depends on u, which in turn depends on x, right? Now that we are chained together, if we view this as one single dependence, if y just depends on x, what is the rate of change in y with respect to x? You might be able to figure out what it is just from looking at them. For every single time that the x wheel goes around, how many times around does the y wheel? Let's reveal the answer. Where's this button where you reveal the answer? Here it is. Reveal the answer. It's 2. Why is it 2? Because 4 times 1/2 is 2. All right. So now that's evidence part 2. And that is going to be, I think, sufficient evidence for us. I'm not going to do a rigorous proof of the next rule that I write down. We're just going to take what we've seen and we're going to extrapolate and say, hey, it looks like when you're trying to study the rate of change in a composition of functions, when you have a chain of dependence between 3 variables, it looks like you just take the 2 rates of change and multiply them together. That's exactly what the chain rule says. So let's write it down. It says, if y is a function of x, but that function is a composition of 2 other functions, s, which is to say that y can be written as f u and u written as g of x, well then, the rate of change in y with respect to x is going to be the rate of change in y with respect to u, first of all. That would be like the derivative of this function. Okay, derivative, right? But then multiplied by the rate of change in u with respect to x, which is the derivative of that function. There. So just take the derivatives of those two functions, multiply them together. But the derivatives are not quite the same type of derivative, which is part of why we're using, the reason we're using Leibniz notation right now to write this down is because in the first derivative, you are measuring the rate of change in y with respect to u. You're not going all the way back and comparing how y is changing as x changes. You're just comparing how y changes as u changes. That's why even though that is a derivative of y and that is a derivative of y, they're not the same thing because they're with respect to different variables. This is treating u as the independent variable. So then this one is the derivative of that u treating x as the. So that's start like thinking about the difference. And what does it mean to take a derivative with respect to something? Because it's like holding, if you hold x constant or if you hold u constant, that's what we're measuring against when we're doing a derivative. So I'll show an example of this in a minute, but I want to first write it down using Newton notation. A little bit harder to do. On the left, I'm actually going to borrow Euler's notation, say the derivative with respect to x of this composition f of g of x. Then on the right, I'll use Newton notation. The derivative of y with respect to u is basically f prime, right? So I'm going to write f prime, but what's inside there is still the u, right? F prime of u, and u is g of x. I could write f prime of u here, except u is g of x. So to make this a little bit more general, I'm going to write f prime of g of x. And then we'll multiply by du over dx. That's the derivative of g, right? So that's just g prime, and that's truly g prime of x. So this prime actually means derivative of f with respect to u, whereas this prime means derivative of g with respect to x. So, so that is how it can be done, okay? So now we'll do an example. And in the next video, I'll do a bunch. Let's use up this little space down here to do an example. Let's say you want to do the derivative with respect to x of sine cubed. Okay, well, first of all, let's remember that what that means is take the sine of x function and cube it. Cube it. So this is a composition of functions. We are dealing here with y equals f of g of x, where f of u is the outer function. If you cover up sine of x with a u, then this says u cubed, right? So the outer function here is u cubed. It's that power function. And then g of x, the inner function, is this one that was on the inside. It's the u variable. It's sine of x. So there is what we have. So now for each of these two functions individually, we'll take a derivative. I'm going to write those in red. So here I'm going to do f prime of u. This is differentiating the f function with respect to its u variable. It becomes 3u squared by the power rule. And here we do g prime of x, getting the derivative of g function with respect to the x variable is going to be cosine of x. And then putting these back together, we're essentially going to multiply these two things together. So the derivative that we're looking for of sine cubed, this is going to be, you could say it's 3u squared times cosine of x. That's just multiplying those two derivatives together. But we want this in terms of x, because it was presented to us originally in terms of x. So we want to finish in terms of x. Along the way, we defined a u variable. U equals sine of x is our sort of, that's what we're sort of basing this on, right? So we're going to substitute back in the sine of x for u right there, giving us 3 times sine squared and then times cosine of x. And that is our derivative obtained using the chain rule. All right. It's been a long one.